All right, I want to briefly review the world of multiple linear regression, which was what you studied in BAS 320, and I'm not going to spend too much time going over the nitty-gritty details and instead talk about what we need to know about regression to pull it off in a data mining context. So there are a lot of slides here. A lot of this is review of BAS 320 just so that everything is in the right place. Let me focus on what I really want you to know for using regression for data mining. So first off, once again, here's what we're concerned about our multiple linear regression model doing. Coming up with a good model that has a small root mean squared error, RMSE, basically is making fairly accurate predictions on new individuals. One way to think of the typical size of the error is with the RMSE, and that's what we've discussed so far. Another way of talking about the typical size of the error is the mean absolute error, or MAE. The difference between the two being that the mean absolute error is the average of the absolute values of the error the model is making. The root mean squared error is the square root of the average sum of squared errors the model is making. The MAE is a bit less sensitive to a few really bad predictions. The root mean squared error is more commonly used, but it does have its sensitivity to a few really bad predictions. Its value gets inflated. The last thing that we sometimes look at is the R squared, basically a number from 0 to 1, 1 being better. If you have a model that has an R squared of, say, 80% on the holdout sample, then for all intents and purposes, you can say that your model essentially gets you 80% of the way there to knowing a new individual's value of y, a very loose interpretation. So we're going to try to develop a model that has the smallest typical error, or the largest value of R squared. And multiple regression is very rarely the model that people end up employing for very large data sets in data mining because there are more powerful options. But let's review multiple linear regression and why it is useful. Well, first, before we get there, let's remember what we're comparing all of our models to. Now, the naive model for misclassification was the majority rules model. Basically, the naive model looked at all the individuals in the training data, saw which class was the majority, and the naive model classified every new individual as belonging to that class. If your model couldn't beat the naive model, then it was pretty much worthless. So, what's the equivalent for the naive model in a numerical response prediction context? Well, the naive model simply says, let's predict for all new individuals just the average value of y among the individuals in the training data. So we can look at the typical size of the error the naive model makes, and your prediction model better be able to beat that. Otherwise, it's a worthless model. So here's what multiple linear regression is doing. First, it assumes that there's a linear relationship between what we're trying to predict, our y value, and each of the predictor variables that we're going to throw into the model. If we were to make a scatter plot of our y variable, in this case top speed, versus our predictor variables, in this case just one, horsepower here, we expect to see that there's a linear relationship that would describe the trajectory of the stream of points. When that's the case, linear regression is the most appropriate and definitely a model worth trying. Mathematically, here's what the multiple linear regression model looks like. It's essentially saying that an individual's value of y is a weighted sum of its features. Its x variables, those predictor variables. With the weights being the betas, these are the numbers that we have to find out with least squares criteria. So that's the goal of the multiple linear regression model, is come up with the weights so that we obtain the optimal weighting of the individual's characteristics that gives us the best estimate of that individual's value of y. Now these features here, the x variables, are left intentionally very vague here. It might be the raw data that's been collected. It might be transformations. It might be functions, combinations of two or more predictors. It's a very flexible model, and when I kind of bash on multiple linear regression and saying it's really not where you want to be, it's not where you want to be unless you have a really deep understanding of what those predictors really should be. Multiple linear regression can pretty much capture any relationship that's out there if you come up with the right set of variables. The question becomes, all right, how do I construct the best set of predictors? Very often that's not an easy question to answer. All right, so one thing to also remember is that even when linear regression is not the most appropriate model, there's nonlinearity in the relationships that you can tell, it might actually still be quite useful. Remember, we have this mantra from BAS 320 that all models are wrong, some are useful. We've employed obviously wrong models all along and still gained quite a bit of insight. So linear regression always is a model worth trying. Sometimes it works out pretty well. Now, the slides I have here are kind of a summary of what you can read off of from our output after you fit a linear regression model, where the weights, the coefficients of each of the predictor variables lie, whether or not those variables are statistically significant or not, those p-values, what the indicator variables representing categorical variables look like, etc., etc. I will have you guys review that on your own time. But one thing that we will look at is the root mean squared error, which R refers to as the residual standard error, kind of an unfortunate terminology. The multiple R squared and the adjusted R squared, these are all measures really on the training data, so we don't care too much about them, but that's where they appear on the summary output from a model that you fit. All right, so let's talk about how those coefficients come into being. How do we estimate what those weights should be going into the model? So what we do is we typically employ the least squares criteria. Basically, we're going to choose the values of the weights, those coefficients, so that the resulting model makes the smallest sum of squared errors possible. So what's the sum of squared errors? Well, if we look at the actual values, the predicted values, this is all still on the training data, we sum up the squared errors, that's going to be the value that we try to minimize. And it turns out that it's really easy to find these numbers from a mathematical point of view, and that's why people have liked this criteria for quite a while. Now, we know that's not the best criteria to be using to choose the coefficients because that's singularly focused on minimizing the model's bias, where instead we want to minimize the model's generalization error. We'll revisit regularized regression shortly. But that's what multiple linear regression is doing. It's choosing the coefficients that the resulting model makes the smallest sum of squared errors possible. Now, how do we get categorical predictors into the equation? Numerical predictors are easy, but we have to trick the regression into treating a categorical variable as a bunch of numbers, and we do that by introducing a set of indicator variables. A categorical variable with L levels requires L minus 1 indicator variables to represent it. They're all going to equal 1 or 0, 1 if the individual has that level and 0 otherwise. So for instance, season, which we might want to throw in as a predictor of, say, product sales. If we have 4 seasons, we look at the one that comes first alphabetically, that's our reference level. Every other season gets an indicator variable to represent it where it equals to 1 when the individual has that level and 0 otherwise. So the indicator variable summer would be equal to 1 if summer and 0 if otherwise. Going back to that R output very, very briefly, this is a model that tries to predict the tip percentage left on a bill based on a bunch of characteristics of the people dining and also the bill itself. And one thing that we'll notice is that weekday is one of the predictor variables. You know, the 4 levels of weekday were Friday, Thursday, Sunday, and Saturday. Friday, you'll notice, is left out because it's the reference level, the one that comes first alphabetically. Notice that we can tell what this indicator variable is supposed to represent just by looking at its form. R appends the name of the level to the name of the categorical variable when letting you know what that indicator variable is. So this variable would be equal to 1 if we're talking about a Saturday and 0 otherwise. All right, so we can get numerical predictors, we can get categorical predictors in there. What do you really need to know for BAS 474? Well, I do want you to be able to interpret the value of a numerical predictor here, the coefficient of one at least, and that of an indicator variable that's representing some level of a categorical predictor. So we'll keep it simple. We'll assume that nothing's involved in interactions. But here is our interpretations. So straight out of BAS 320, if X is a quantitative feature, quantitative predictor, in order to interpret its value, what we say is that, okay, 2 otherwise identical individuals who differ in that predictor by 1 unit are expected to differ in Y by beta units, the coefficient of that predictor in the regression. If the coefficient is positive, the individual with the larger value of X is expected to have the larger value of Y, etc. Now, what did this otherwise identical kind of term refer to? Well, it refers to the other predictors that are in the model. So we're assuming that the individual has the same values for all those other predictors. They only differ in X by 1 unit. Well, that's how we interpret the coefficient. We assume that they are identical except for that one variable. When they differ in that variable by 1 unit, we expect them to differ in Y by the coefficients units. Go ahead and write this down on your sheet of notes for the final exam because you know you're going to have to interpret a coefficient. What about if we're dealing with an indicator variable representing a categorical variable? Well, here's how we interpret that. One thing that we note is what the reference level was, whatever came first alphabetically, because the interpretation always is tied in to what's going on with the reference level. So when we're asked to interpret the coefficient of an indicator variable, we say that, okay, among otherwise identical individuals, once again, same values for every other predictor in the variable, the one with level j, the one represented by the indicator variable, is expected to have a value of y that is beta higher than the one with the reference level. So that's assuming that beta is positive here. So reference level is the one that comes first alphabetically. The level that we're trying to interpret is the one represented by that indicator variable. The coefficient simply tells us, all right, how much higher than average or how much lower than average compared to the reference that individual's value of y is expected to be. All right, so there's a few slides that kind of go over that sort of interpretation, but that's what I want you to be taking out of these slides. Be able to interpret a numerical predictor's coefficient and an indicator variable's coefficient. Now, I said that we're keeping it simple and ignoring interactions between variables. One thing that we know is that interactions play a phenomenally important role in almost every relationship. And so interpreting coefficients in the presence of interactions becomes a lot more difficult. You learned how to do it back in BAS 320. I'm not going to revisit that here, but I am going to remind you what we mean by when two variables have an interaction. So when two predictors have an interaction in the model, that basically means there's an additional predictor, the product of the two, in the model as well. And having that additional predictor allows us to accomplish a few really important effects here. Number one, it allows the strength of the relationship, say between y and x1, to actually depend on exactly what value of x2 we're talking about. For some values of x2, the relationship between y and x1 might be strong. For other values, it might be fairly weak. So looking at an example of that visually, this you saw a lot in BAS 320. We were looking at the relationship between someone's salary, say, and the amount of years of education that they had when they were applying for the job. And what we saw was that education and experience had an interaction. We couldn't just say, all right, two people that differ in education by 1 year are expected to differ in salary by a certain amount, because that difference depends on exactly what value of experience we were looking at. So how is this interaction working? Well, what we notice is that if we focus in on individuals with a large number of years of experience when they were applying, the red line here, there's basically no relationship between salary and education. It's basically flat. An additional year of education doesn't buy that individual any additional bit of salary. However, if we look at individuals with small values of experience when they applied for the job, well, now years of education matters quite a bit. Two individuals that differ in education by 1 year are expected to differ quite a lot in terms of salary. The individual with a larger value for education has a much larger salary than the one with the lower value of education. So what we see is that the importance of education, sometimes matters and sometimes doesn't, depending on what the person's educational value or experience level was. So very often interactions play an important role in relationships. They're really hard to get into a regression model just because with a lot of predictor variables, there's just so many interactions that you'd have to try out. So many new predictors, the products of those two variables in the interaction, to try out that it's really just not worth your time here. So anyway, know what interactions are. I'm not going to quiz you too hard about them, but they're very, very important here. All right, so how do we actually use multiple linear regression for data mining? It can be a very powerful model if you throw at it the right predictor variables. Very often we're not going to have the right predictor variables, so we'll come up with an inferior model. But like this model right here shows, sometimes an obviously wrong model might still actually be really quite useful. Here our straight line model is very wrong. Linear regression is not the way to model this curved relationship, but the predictions actually get pretty close. So what do I need you to know for data mining with linear regression here? Well, it has some pros. First, it's an easily interpretable model. In fact, it's really the only one that we can do descriptive analytics fairly easily once we fit it. We can actually talk about what the relationships look like. Making predictions is very easy. You just plug in numbers to the equation. And it's really the only statistical model that we consider where we can get confidence intervals and a lot of other things that statisticians care about. A lot of cons associated with this. Normally, or mainly, interactions are very difficult to fit into the model. The coefficients of the model are chosen just to minimize the bias. We can fix this with regularization. But it's the most difficult things are, okay, what are the interactions we need to be putting in, and exactly what should we be using as the predictor variables? The recorded values, transformations, combinations. etc. Going through and trying out a whole bunch of different regression models that have or don't have various predictors usually just takes way too much time. And so there are better options out there. All right, so there are a few slides that talk about how you can actually go about figuring out what variables you should be putting into the model with a technique called backwards feature elimination that's implemented in Carrot as well. It's very hard to get to work. It's not the fastest thing either, so I'm just going to leave that there to let you know that it exists. Now, the last thing that I want to do in this little mini lecture here is to talk about how we fix some of the problems with multiple linear regression, and that's by applying regularization. So the problem with least squares regression, which is that standard multiple linear regression you talked about in BAS 320, is that the coefficients, the weights of those predictor variables, are being chosen solely to minimize the bias of the resulting model on the training set. Now we know the estimated generalization error also involves the model's variance, not just its bias, so we should be picking out these coefficients to reflect that. And so this is what regularization accomplishes for us. It says, okay, yes, minimizing the sum of squared errors is important, but also minimizing the resulting model's sensitivity to the training data, kind of minimizing the model's variance here, is also going to be an important feat. So what we're going to do is we're going to apply a penalty based on how much information you're actually extracting out from the individuals in the training data. And so when we use R to do this, we'll use GLMNet here, and we'll use a mixture of the ridge regression and lasso approaches. So the coefficients that we'll choose for our regression model are the ones that provide a good balance between the bias and the variance. In other words, they give the smallest value of the sum of squared errors plus the penalty based on the complexity of the model. The complexity penalty lambda here plus some sort of penalty based on the sum of squared coefficients plus some sort of penalty based on the sum of the absolute values of the coefficients. When we do regularization, we scale each predictor variable to have a mean of 0 and a standard deviation of 1. So the sizes of the coefficients tell us how much information we're extracting out from that predictor variable. The more information we extract out, the more we're making our model sensitive to that particular predictor variable and the individual's values that reside in the training data. And so it's a good idea to penalize the amount of information that we're extracting. In order to use a predictor variable, well, it really needs to contribute a lot of information about what we're trying to predict. So we figure out what the optimal penalties are for the complexity and the mix between ridge and lasso regression with that k-fold cross-validation. And almost always, we get a better model out than the vanilla multiple linear regression. Why is that the case? Well, one thing you'll notice is that if lambda is equal to 0, then we're just doing least squares regression. We're minimizing the sum of squared errors. So in some sense, multiple linear regression is really just a special case of doing this regularization procedure. And since we'll let a very, very small value of lambda be a possibility, one that we'll consider, we'll be able to consider multiple linear regression in its vanilla form while we're doing this regularization. So you can refer to the guide for how you kind of go and try out all these models to get examples of doing regularization. But one cool thing about doing regularization is when you have an alpha equal to 1, basically doing the pure lasso, it does a bit of feature selection for you automatically. I just said it's very difficult to know what predictors should be in or not in a model. Well, if you set up that alpha to be equal to 1, so it's doing pure lasso, what it will do is it will set to 0 some predictor variables that it doesn't think is very important. For other values of alpha, it doesn't necessarily do this. Alpha equals 1 is the key here. But in the model, we're predicting the baby's birth weight based on a bunch of physical characteristics of the mother and the father, whether or not the mother smoked, etc. We can go back and ask, hey, Lasso, what predictors didn't look like they were important? Which ones did you assign 0 coefficients to? And in that case, it actually spits back 8 variables where it says, hey, it doesn't look like it's all that important. All right, so that's how we use multiple linear regression for doing data mining. There's a really cool additional aside that I'm not going to go into for doing non-parametric regression where we don't actually say, all right, here's the equation I want to fit. We actually let the data figure out what curve best goes through the stream of points. But I'm just going to let you review those slides on your own. First, it's only useful for when we predict a particular value of y from one predictor variable. When we have more predictors, we can't really do this. But it's a really cool technique, basically saying, okay, well, let's not just impose a straight line on a stream of points. Let's actually let basically the data figure out what's the trajectory look like and all the wiggles and bumps that you want here. So there's the lowest, we have the spline, which are two different ways of doing this. There's a smooth scatter plot, which is a really cool thing to look at. Neat thing to know, but we're not going to be using it much in data mining. It's more of a graduate level concept here, but it's something that you might be interested in, might be useful for your own queries. All right, so next up is going to be the rest of the models that we've talked about for classification, just for doing numerical prediction.